Okay, so welcome everybody to the last colloquium of this semester. What does that mean? Okay, so today we have as our guest Heino Falcke, and so Heino has started his career with PhD studies with his advisor, Professor Biermann, at the MPI for Radioastronomie in Bonn. And then after several stations, including Tucson, Bonn again, he landed in Nijmegen in the Netherlands, just across the border. So it allows a good collaboration between the Netherlands and Germany, I guess. Then he became there a bijzonder hoogleraar in 2002, then a professor in Cologne, and then also a full professor. He's now full professor at the Radboud Universiteit in Nijmegen. He's also chair of the board of LOFAR. He has received several awards, starting in 2000 with Ludwig Biermann Prize of the Astronomische Gesellschaft. Recently, he obtained in 2008 European Research Council Advanced Grant. And in 2011, he received the NWO Spinoza Award, which is the largest, most prestigious award for science in the Netherlands. And it gave him the opportunity, I heard, to meet the future king and queen of the Netherlands and actually have dinner with them. Oh, lunch, okay, but the future king means in April already. They are going to be so. He actually also speaks fluent Dutch, so that's also very commendable. I think, as a Dutch person, I have to say that, and since he's professor in the Netherlands, so okay. Ah, right. Okay, so without much further ado, I would like to welcome Heino here to Heidelberg.
Yeah, thank you very much. And actually, I did point out in the early days of LOFA, we had this PR picture in the background here. So this was the original idea of LOFAR. This was sort of the Netherlands, and then there's a big ocean, and then the rest of Europe here. And luckily, this has changed significantly now that LOFAR is A, now a reality, and B, it's actually a nice European project with a lot of very active people. A lot of young people active in this collaboration, in this project actually, throughout Europe. A lot of in Germany, of course, a lot in the Netherlands, but also in many other countries. And this talk will be a disaster. I have to apologize right away. So I used to have talks saying how great LOFA will be. And so, but in the last couple of weeks, we got a lot of nice new results, and I tried to show them all, and then I realized it's going to be way too much, so I threw them out again. So I'm not going to do any good service to the people who have obtained those results, and hopefully, well, I hope I'm able to explain a few things, but it will be many different areas I try to address, not just talking about one particular topic. So that's the nature of these telescope talks, right? So you talk about a broad range of subjects. Let me introduce the telescope a little bit. And so there are two ideas that led to LOFAR. The first one was that the low frequency range in radio astronomy, that's where radio astronomy started in the early days, so around 100 megahertz, a little bit below, a little bit above, had been completely deserted over the last decennia, actually. And so the idea was, let's go back to there and see whether we can improve things. The second thing was the digital revolution that's there, because what we actually have in LOFAR is more or less a virtual telescope. If you look at the Effelsberg telescope built in the 70s, it's one big dish that works as a collecting surface. Then it focuses the radio emission in one point, and then that's where you have your receiver. What we do now, well, then you had, of course, the interferometers, where you actually had many little dishes which were working together as an interferometer, and you used those in order to make an image. Essentially, You use every baseline between two telescopes as a little interferometer. You measure interferometer fringes, and as the Earth rotates, you can then get the structure of the source that you're imaging. And you would look at sort of individual sources, one by one, with those interferometers. And LOFAR is now the extreme, because what you now do is you replace the entire dish here by receivers. So you don't have a dish anymore, you only have receivers, no dish. And the reason is that you can actually digitize radio waves completely, and you have your receiver will then receive radio waves from all over the sky, and by combining them, you can actually combine them in your computer in such a way as if your dish would be pointing this way or that way. You essentially do, you could say, ray tracing in the computer with your digitized waves. And that gives you enormous flexibility. And that's something that attracted me early into the project, to have these capabilities. And so there are actually two things I was personally dreaming of, apart from the science that I will address, that I would like to have a really versatile telescope, because that telescope allows you to look in all different directions without changing a dish, moving a dish. So you only have to switch your computer. You can actually look in different directions at once. You can have different types of beams looking at the sky. And so that gives you a whole element of freedom and creativity that I want to have. I wanted to have a telescope that is, that lets your creativity, freedom. And I think that was shared by a number of people and has been realized now. And the second one, I think at the time when this started, radio astronomy was a little bit in a low. And what I was hoping for, that this would actually lead to a vibrant community again that sort of uses these, especially these low frequencies. And I think that's also something we are seeing at this very moment. So how does it really look like? Now, when I give a tour of telescopes or so, recently I was sort of accidentally again in Effelsberg leading a group of people, showing around people, and then I looked at the dish of Effelsberg, and I was explaining the LOFAR station. While I was explaining LOFAR, everyone was looking at the beautiful dish. So it was very frustrating. And that's, the reason is obvious, because that's it, right? So this is essentially here a piece of wires and a plastic rod here and a little amplifier. This is our low band antenna, so we have thousands of those. And then we have at the high band antenna, we have styrofoam and casings with, again, crossed dipoles in there, which have a little triangular shape to be a bit more broadband. And these things are relatively cheap and relatively low cost. All the energy and the engineering art and the money essentially goes into the digital electronics and the software. So what you then do is you combine those antenna elements. These are the low frequency antennas, the low band antennas. These are the high band antennas. These are the tiles into what's called a phased array. And they are collected here in one station. So these are 96 of these low band antennas, and again 48 of these high band tiles. And of those stations, 48 are planned, 45 are now operational and working. One is constructed and will be sort of validated soon, and 2 more are left hanging in the bureaucracy in fighting with landowners and so forth. And in addition to those, in part of those 45 stations, 8 of those are international stations, which I'll show in a moment. In the very center of LOFAR, those phased array stations are actually combined into one big field. It's called the Super TERP. Now, TERP is something like hill in the Netherlands. Now, a hill in the Netherlands is 2 meters high, and that's exactly what it is. It's sort of, that was in the swamp, a little hill where you could defend yourself against the enemies. And that's sometimes still the thinking in this part of the country. But, this now has changed quite a lot. Sorry, you did tape that statement. I think you should take that out. That's okay. And so these are the innermost 6 stations in LOFAR, the Super TERP. And actually also contains cosmic ray detectors, because what we also do is cosmic ray detection. If I have time at the end, I'll talk about this, because that's also quite interesting and quite different from normal astronomy. And then here you have an international LOFAR station. You see it's bigger. Bigger means smaller field of view, but more sensitivity. And you need the more sensitivity in order to calibrate on the long baselines, because you need cosmic sources to calibrate on, and therefore more sensitivity is needed. And then, all this combined in one picture in Europe. This is the sort of distribution of stations. We have here a lot of stations in the Netherlands, 37 at the moment. And then in England, France, in Germany, 5, and the 6th station in Hamburg is to come. And that is very important because it fills an important gap here in the distribution of stations. Small separations give you low resolution. Large separation gives you high resolution. And the more filled the space is, the better the image quality. And so there's one baseline that's missing that we filled. And then Poland actually also probably has money to build additional LOFA stations. So actually it's quite a nice array and has very small separations in the superturb from tens of meters to actually thousands of kilometers. And that allows you to probe all kinds of spatial scales. It's quite unique. If you know the VLA, for example, it does the same over a much smaller range, but they always have to move telescopes. We have it all at once all the time. So that's quite luxurious from a point of view of a radio astronomer.
Do those lines have meaning?
No, they are just nice white lines sort of drawn by an artist. But not quite, because as far as I understand, actually the German data connections are going through Jülich. Where there's a fast connection to the data center in actually Amsterdam. So it's not exactly as it go. In the end, actually, the data correlation and processing is happening in Groningen up there. So there are different actually data centers which play a role. Jülich does play not only a role as a station provider, but also as a data center for Germany. Yes. And then the flexibility, let me talk about this a little bit, because every element you can actually use individually. One single antenna, of course, is not very sensitive, but it sees all the sky at once. That's what a dipole does. And in fact, we've built in so-called buffer boards, which allow you to store the raw data of each individual antenna. And so if something happens, like short flare or so, we can store this buffer board data, read it out later, and recover actually the radio emission in any direction we want. Within a certain short time scale, currently it's 1 second, soon it will be 5 seconds. So if there's a fast radio flare somewhere, we can actually point it everywhere in the sky. Enough time, if I have time, I'll show this. And then you can combine the antennas, do interferometry within the antennas in the station. Then you form a station beam, and then you have higher gain, more sensitivity in one direction, but smaller field of view. Well, smaller field of view still means that you have several tens of square degrees that you have in each station. And then you can combine the beams of individual stations, again, interfere them, and then you can get, for example, a tied array beam, and that means essentially just a single pointing in one direction, which can be very small. But this you can do multiple times. You can sort of point them in any arbitrary direction, or you can put them all together. And so in total, you get sort of 100 times, actually now it's 250 times, 0.01 degree, so you get, again, 1 square degree by just having all these individual little beams. And then what's not shown here is you can correlate the data from individual stations, and that allows you to make an image of the sky simply by Fourier transforming within a field of view of the station beam. So that gives you a rather large field of view with actually the resolution of those tied array beams. That's rather complicated, and allows a lot of different things to be done. I'll skip that part. There are challenges, of course, if you have a phased array, and that is that the thing doesn't move. Now, if a dish moves, it essentially more or less keeps its shape. I mean, there's a little of gravity working on it. You can compensate for that. But here, if you're looking at the horizon, your sensitivity is significantly reduced. Your beam will change. So if you look towards the zenith, you have a very different beam as when you look at lower elevation. So that's something you need to compensate for. That's in principle just software, but software costs a lot of work. And in fact, it has still not been perfectly implemented in LOFAR. The second one is the ionosphere. This is actually an old image showing 2 different sources on the sky from the GMRT telescope. And you see how you have ionospheric seeing. That's just the free electrons in our atmosphere, 80 kilometers high. They have fluctuations like you have in the optical seeing, which will sort of move any source around. Instead of having 2 nice point sources, you have 2 blobs wandering around. So you need to be able to calibrate this. You can do this with an existing model, for example. There are 2 point sources, and then you can calibrate and track what the ionosphere does, and then go deeper and deeper and have an iterative process. But it's not it's not that easy. And then lastly, this is interference. So what I show here is time. This is spectrum. Is frequency. There's a low frequency part. So this is 35 to 75 megahertz. And this shows occupancy. This is which part of the spectrum is occupied by terrestrial transmitters. This could be, you know, a car or whatever, some other radio transmission. Certainly, you know, if you go above here, 80 megahertz, and you have FM band transmission and so forth. And so you see there's a lot of stuff going on. But if you look at the scaling, then this is sort of 5%. So most of this is at the 5% level. And so at most 5% on average of the data is interfered by external transmitters. In the old days, when you had an analog transmitter and no way of knowing, really having good spectral resolution or time resolution, your imaging, whatever, would have been completely screwed. Now, with digital technology, you essentially just, you know, whenever something is on, you just ignore the data. That's very easy. And so interference actually is the least of our problems these days. It's quite interesting, this development. Enough about, well, a little bit more about organization now, and then we go to the science. The way because we wanted to have a very flexible telescope, we had actually a number of key science projects that would get some of their science done, but that would also drive the design of the telescope, and in very different directions. And so the main key science projects were the epoch of reionization. I'll explain that. This is sort of very deep imaging, very of the very distant universe. Then surveys, so making large field of view imaging, many sources. High energy cosmic rays, very short radio flashes of a cosmic ray hitting the Earth's atmosphere. Looking for transients and pulsars, radio sources which suddenly flare up and go away again, or pulsars, rotating neutron stars. Look at the magnetic fields in the interstellar medium of our galaxy and of external galaxies. And that is because of Faraday rotation. Faraday rotation is when the polarization of a radio vector, of a radio wave is actually rotated in the interstellar medium by the presence of magnetic field in electrons. Now that leads to a rotation of the polarization vector. And that allows you to measure very precisely the magnetic field. And then the end solar physics and space weather, of course, the sun is a very bright radio source. One word on organization. The way it works, actually, it's very complicated. LOFAR is actually owned by a company. It's rented out to a foundation under Dutch law. And that foundation, this is the sort of has a board which actually really organizes the science and the exploitation of it. This is fed by national consortia. So there is a German LOFAR consortium, a Dutch LOFAR consortium, and Astron as the main institute which built the telescope has similar say. So the Dutch vote actually is 3, while the international ones is 4 in the board. So actually there are more international people in the board than there are Dutch representatives. Okay, so talk about the science. And I'll start with pulsars because the pulsars have been the most, I would say, advanced in many areas. Because they have been a small group at Astron really working hard on this, and it's one of the first things you can do. And this shows nicely actually the progress we made. In 2010, actually, the telescope was officially opened by the Queen. And you see here a pulse measured from a pulsar. And you see, you know, this little pulse seen and a lot of noise. And then 2011, when more stations were brought in, were calibrated, sensitivity got better, and now actually you get a very nice and clean pulse. In fact, the data quality is now really good, and certainly has improved once more over the last couple of weeks when more and more stations were calibrated. Essentially, you have to look at think of the individual antennas as elements, for example, in a mirror. And until sort of 2011, many of these mirrors were not properly adjusted, so just, you know, roughly adjusted. And now they're all perfectly aligned by proper calibration things. And so they did a number of interesting measurements, and I actually had many more slides on pulsars, and now I'm left only with 2. And so one interesting surprise was about the low frequency emission itself. If you look at the pulsar is a neutron star which rotates quickly, and the ones we were mainly looking at was around 1 second pulsation periods. And then you have actually a radio emission coming. The idea is that they essentially is produced along this dipolar structure of the magnetic field. And the idea was that the high frequency emission is produced close to the pulsar, the neutron star, and then the low frequency emission further out. And then the neutron star, of course, rotates, and then you get a pulse every time this sweeps over you. And you get two, if you have sort of here a diverging magnetosphere, you get two pulses. This is what you see here. And you would expect then, as this magnetosphere sort of opens up, that the low frequencies pulses are much wider than the narrow frequency pulses. And that was the first time that people looked at sort of from 8 gigahertz all the way down to 40 megahertz at a single pulsar to see essentially many orders of magnitude in frequency range. And what you see is that essentially the width of this pulse, despite this many orders of magnitude, doesn't change much. So really this model that you would have this stratified emission doesn't really work. What you also see is that they all arrive essentially at the same time. If you have things widely separated emission mechanisms over the magnetosphere of the pulsar, then you would expect relativistic retardation effects. There's a delay for the radiation that is produced out there and the one which is produced here. And that's also not seen. And that suggests that all the emission comes within sort of 60 kilometers, so a few neutron star radii only, so very close to the neutron star. And so that was, to some degree, a surprise. In fact, quite a number of pulsars don't really obey this broadening at all. So that really needs to be rethought. And that's a paper that came out last week in Science. Another surprise, so to speak. Another model, if you go back, another basic idea was, okay, you produce here beams of electrons which produce the radio emission. And then, radio emission is produced, and you have electrons and positrons, and I think the positrons go out, the electrons actually go back to the surface, and they would heat the neutron star surface and produce an X-ray emission, thermal X-ray emission as they do this. Now, what we see here were simultaneous LOFAR, GMRT, and XMM emission measurements of a pulsar. What you see here is, again, these are many pulses. This is time. This is pulse phase, so that's where the pulse is. There are actually many little pulses which are seen here. And then suddenly the pulsar switches off at this point. Actually, it does so within 1 or 2 periods. We actually see in LOFA individual pulses. We don't have to integrate long time. So it's a very sharp switch off of the low frequency radio emission. And then you would expect that the X-ray emission, also switches off because there are no electron beams hitting the surface. Quite the opposite happens. So the radio emission actually goes into this quiet state, and then the X-rays turn on and show a thermal spectrum. And that's sort of very hard to understand and pulsate. And they also pulsate, that's also hard to understand because you expect for this pulse that you look right head onto the pole. How can it pulsate? This can actually only happen if you obscure this region somehow. That's a big puzzle. The idea is that actually within those few seconds, the entire magnetosphere rearranges itself and makes the polar cap visible or hides it. And that's quite a feat for such a neutron star with one pulse period or so to change its magnetic field so quickly. Of course, what you want to do is pulsar surveys, and that's going on as we speak. The prediction is that we're going to find about 1,000 new pulsars. And one of the goals is, of course, to find a black hole neutron star pulsar. This would be a really golden pulsar because you can test many predictions of GR with such a system. It hasn't been found yet, but if you can double sort of the number of pulsars with LOFAR, the chances would increase. A first Pathfinder pulse survey has been made. We found 10 new pulsars. This was very frustrating because of the 8 first one we found out that a few months earlier another telescope had found them as well. So we have to claim joint discovery. But now, like 2 weeks ago, we found the first one, which are really unique. So at least there are 10 new ones. And if you extrapolate further with this cycle 0 survey that's going on, we should find actually 100 to 200 new pulsars in the next couple of months, at least to the end of the year. So, that's really looking good. Now I want to switch to another topic, and that is spectral lines. And you probably would have not thought of LOFAR as a spectral line telescope. But what we've been doing in the pulsar observations, we use this tide array beam. We use all the antennas, combine them, and make LOFAR work as a single dish. And then you get sort of the radiation from that pulsar at high time resolution. And then you look for periods and pulses and so forth. That's what you do. But of course, you could also use this single dish as a tool to do spectroscopy. You can use the same data, more or less, and do Fourier transforms and make a spectrum of the emission in a certain direction. And then you can do spectral line studies at high spatial resolution. You can do the same also with this interferometry mode, but here it was done to some degree with this tide array beam mode. Some of that was also done with imaging mode. But okay, so what you see here is actually an image of Cassiopeia A made with LOFA at 60 megahertz, the Supernova Remnant. That's the first pretty image, actually. We were quite happy to have that image because at 60 megahertz so far, all images were just blurred, right? There was nothing. It was just a little blob. So you really see an image that looks like something you see in other wavelengths nowadays. Because, of course, low frequencies is long wavelengths. You typically have poor resolution. So that has certainly changed here. And then, you can look actually for absorption line spectra in towards the source in case A. And what you see here is carbon 576. So this really is a Rydberg atom, so very high levels, electronic levels, where essentially it's almost an ionized carbon atom what you have here. But it's still mildly bound, and actually these kind of atoms can have a fraction of millimeter size, right? So large are they. And so you see a nice spectral absorption line towards case A for this one particular line with a delta V of 1 to 10 kilometers. So that allows you to suddenly look at the interstellar medium. And what's nice of these Rydberg atoms is, because you have so many levels, they're essentially almost all identical. And you have many of them within your band. So even if you don't have a very good sensitivity on one particular one, you can actually sum up several of them. And so what you see here is actually the sum of 47 carbon alpha lines. And here's this carbon beta and this carbon gamma. So there's 60 or 76 lines, all added up together at different frequencies. This is well defined. I mean, that's just atomic physics. And then you can line them up, and then you can get sort of your line. And they essentially all tell you the same thing. And so if you look at this, you actually learn something about interstellar medium gas at very low densities, sort of about 1 particle per cubic centimeter. Of course, because if you have such a large atom and you would have dense gas, they would collide and you wouldn't have any Rydberg atoms left anymore. Okay, and there's a very low tau. It's of about 10 to the minus 3 to 10 to the minus 4. And one thing I just thought about last couple of weeks, because that is, again, hot off the press, just 2 weeks old or so. You should be able to use this even as redshift indicator. If you have a very distant source, if you stack up all these different lines, actually just a different redshift should allow you to determine the redshift. Even if you don't know exactly which line it is, just the separation between the lines should give you a redshift. So that's something we want to try later this year. And because that would be cool, because then you could actually get redshift towards radio sources which are optically not identified. And that'd be quite interesting in the future. No, well, that's sort of, I'm not promising this is going to work, but something that's sort of interesting to keep in mind. Staying in the interstellar medium, this is an image we actually made in the Transients Key Science project just to monitor a microquasar, which happens to be in the center. In fact, this was a program where we had 7 beams on one field, and we had 1 beam left, so we put it on the microquasars just to have fun. So it doesn't have much sensitivity. But what you see here nicely is actually the structure in the interstellar medium. And sort of some actually may know from the shape what that is, because that is the Heart Nebula, which you see in the optical very nicely. And this, I'm not even sure what this is. This, again, is just a few days old. It may be free emission probably, which we see there at low frequencies, which is a bit unusual at these frequencies. This is the Supernova Remnant that you see there in this image. Now, what you want to find out, and that's one of the, so that's sort of unplanned, and we have to sort of, I don't know whether we can do anything scientifically with it, but that's something you can do scientifically with. So that is an interesting measurement. That is a fan region. That's, again, a particular region in our Milky Way, actually 8 degrees above the plane. You're looking into a field, and it's known to have a lot of polarization structure. And as I said, polarized emission is affected by the hot electrons at magnetic fields in our Milky Way. So you start with a polarized wave, and then it goes through the interstellar medium, and then it starts being rotated. And that rotation is a function of frequency. So different frequencies are rotated differently. That goes with the frequency squared, or lambda squared, more or less. So what you can do is, if something is produced very far away, yeah, it's rotated that much, and if something is rotated close to you, it's rotated a little bit less. And that, again, is a function of frequency. And by looking at different frequencies, and looking at different lambda square laws as a function of frequency, combining the different frequencies in different ways, you could essentially look at different parts in your Milky Way and see different structures. That's called Faraday rotation synthesis. So you get actually a third dimension in your picture. And so that is for one particular rotation of the electric field. And then you go a little bit further, then you suddenly see a lot of structure in just in the polarized light. That you don't see in total intensity, just polarized light. And then you go further and further, and suddenly you see sort of a little ring, and that's a clear bubble which you suddenly see in there at a certain Faraday depth. And that, that may be, and so it's not clear what this is, but actually, if you look at any LOFAR image, you always see structures, not necessarily rings, but all kinds of structures from the interstellar medium in there. So this might be one idea, this might be just random sphere, like just 200 parsecs away, sort of along your line of sight from a perhaps white dwarf or whatever. Yeah, I'll skip that part of the interstellar medium. There's more to be said, but I'm sorry. Now, I'll leave the galaxy, and then, of course, you want to make images not only of ourselves, our Milky Way, but also of extragalactic sources. And so this here is, again, this is pretty crappy data of the Virgo cluster. And so this is 140 megahertz, and we chose the Virgo cluster not because it's easy, but because it's hard, to quote J.F. Kennedy. And the reason is why it's hard is because it's low elevation, and it's a very bright, this is one of the brightest sources, M87, it's 10,000 Jansky or more. So that gives enormous dynamic range problem. We want to see whether we can do anything at all in this range. And that was part when we still had very uncalibrated telescopes. This is when 5 by 5 square degrees. You see M87 here in the very center. That's the central cluster of the Virgo cluster. And then lots of other galaxies surrounding it. So this is a zoom into this. So you actually resolve the individual galaxies in here. You have them all at once. And then you can zoom further, and you can actually see this very nice structure of M87. Of course, the bubble itself was known from the VLA before, but at these low frequencies, I think has never been imaged at this quality and beauty in the, ever. And so if you put things together, just for those who are not familiar with M87, this is actually a composite SDSS and LOFAR at 140 megahertz. And then you look at the higher frequency VLA map, you have this nice jet coming out of the very center. And then you zoom into this core, you actually see the jet down to, actually nowadays down to almost a few Schwarzschild radii that you can trace down. So that is a jet produced by a supermassive black hole, 4 times 10 to the 9 solar masses, and that inflates this entire bubble and fills the entire thing. What you now can do with LOFAR is sort of make spectral index maps. These are maps at different frequencies, 36, 48, 59, 71. And you make a spectral index map. You see a sort of flat spectrum in the center. Flat spectrum usually talks of freshly injected electrons. Steep spectrum usually are aged electrons because high energy electrons, high frequencies, lose their energy first. They radiate the most, and so thereby they're gone quickly. And so a flat spectrum starts to steepen in the radio very quickly. And then you can look at different regions. And this here is actually quite nice to show. These are sort of the measurements at higher frequencies, and this is LOFAR, which covers the entire frequency band. So we're not just getting one single spectral point, but we get the entire. Of course, I mean, a bit disappointingly, this one is just a pure power law. I had expected actually at low frequency, you expect many sources to turn over because of electrons running out at low energies or of self-absorption. That is not seen here, but you see sort of a little bit of curvature here towards the high frequency. You can use this then to determine magnetic fields in these bubbles and powers and so forth. And so what you find in M87 is energies, magnetic fields about several tens of microgauss. And interestingly, an equipartition energy of the jet power of 6 times 10 to the 43 ergs per second. That's what you would infer from magnetic fields being in equipartition. But if you then look at the gas that surrounds this bubble, then you know from X-rays what the pressure is. And you see that the pressure actually has to be a factor 10 higher to sustain this. So you need to have a bit more energy inside this bubble in order to keep this thing maintained. Otherwise, it would just collapse. What's also actually was very surprising to me, because old low-frequency emission is old electrons. I would have expected that we would have seen a much larger bubble than you saw that in the past at the VLA, for example. We don't see that. It's essentially more or less all contained. And you look at time scales of M87, and the dynamical time scales is about 40 megayears. The synchrotron age time scale is 25 megayears, so it's all several tens of megayears. And we've checked, we should have seen old relic fossil emission several 600 megayears old. So it looks like this thing is relatively young, the Virgo M87, like 10, 30, 40 million years, which I find a bit surprising that over the last sort of half a giga year, M87 was only on in the last 10% of its lifetime when we were looking at it. And M87 is a very special, it is this central galaxy of the closest cluster in our neighborhood. So it's a bit puzzling whether we are really living in a special time or there's something else happening in terms of physics. Certainly we expect in other, and I know in other sources, that we're going to see relic and past outbursts as well from those supermassive black holes. I'm skipping all of this, and someone's going to be bad at me. Now we go even further. Now we go to actually a more or less random LOFAR field. This one was M87, Virgo cluster. Now we go into a field which is mainly extragalactic. Again, this is old data. And so this is inner 3 by 3 degrees. This goes down to 0.8 millijansky. If you remember, in the very old days, you would have essentially Jansky emission would have been, sensitive measurement at these frequencies. Now really at sort of millijansky levels. This is close to the thermal noise. You actually, in the entire field of view, you see 1,000 sources at this moment. And if you zoom further in, so actually see, there are sources all over the place. And in fact, every LOFAR image you have will look like this. It will be full of sources. You just can't help it. And what we noticed was quite interesting. If you look at it, there are all kinds of these double sources. Doubles. And that's no coincidence. So we checked, there's sort of, you would expect 5 random matches from all these sources in this image. There were 33, so it's highly overdense doubles. So what this is, essentially are something like this. This is a LOFAR image of Cygnus A. Again, the supermassive black hole, radio jets, 2 hotspots at the end, and that's it. These are the brightest radio galaxies in the universe. And you can then calculate whether and what you can see. These sources are only made if you have a supermassive black hole of order 10 to the 8 solar masses radiating at Eddington or close to Eddington. So there's a minimum power to make these things, because you need a minimum power to get out of your galaxy. These, as you see here, this is the X-ray emission. So this one has pierced out of the X-ray environment, the hot gas of surrounding the galaxy. So there's the minimum power needed. These are always the brightest ones. And you can actually show that in every LOFAR image, you should be able to see an average FR2 all the way out to redshift 2 to 3, and a sort of bright one out to redshift of 10. So essentially, you would see all FR2s in that direction that you're looking at. And secondly, these things, when they go out of the galaxy, are typically 300 kiloparsec in size. 300 kiloparsec is about 20, 30 arcseconds separation. And we had sort of 10, 20 arcseconds, so we can just resolve them. If you look at the cosmological evolution of a ruler, which is 300 kiloparsec, from redshift of 0.5 to redshift of 5, the angular size does not change much. It's always about 20, 30 arcseconds. It's just a coincidence of cosmology. So essentially, all FR2s in the universe will have roughly the same size in your image. So they will all be. So you see them all, they should all be there. So we thought that might be an interesting tool to explore, because it's easy to just count them. And we called them, by the way, dubbeltjes. This is a Dutch word, sort of doubles, little doubles. It's actually 2 5-cent coins. So counting dubbeltjes, something the Dutch do like to do, because it's counting the money. And that may be actually quite interesting. So that is sort of a first attempt at this. I'm not saying that this is sort of complete. We're working at this as we speak. So this is a log n, log s, some number of dubbeltjes as a function of flux density. These are the red points here. And then the red line is a very simple model where we take a quasar luminosity function, which tells you how many quasars at what redshift have which luminosity. You convert that to a jet power through a sort of jet disk coupling that we know from the local universe. So much energy goes into jets, produces that much radio emission, and then you can predict how many dubbeltjes you expect. And that works reasonably well, all the way out to redshift of about 1. We're missing a few at the brighter end, but that's not surprising because we have sort of an upper cutoff of separations. But at the low flux end, and that is really well above our noise limit at redshift of 1 to 2, suddenly the dubbeltjes become less than we expected. I've seen that, I'm already scared, so it's so that's going to be interesting. So it may be that there's some mechanism that suppresses those. For example, that the density of the interstellar medium becomes much higher, and thereby it becomes much more difficult for them to move out. So we're going to explore this further. Just to show one thing on the high resolution side, this is an image actually which was made of, again, a similar radio galaxy, radio jet, with now using not just the Dutch part of LOFA, but using all international stations. And so that here actually has a smoothed resolution. So this has 0.3 arcsecond resolution that we can get down to sub-millijansky sensitivity, which is, again, quite a feat. I mean, to this low flux limit to get sub-arcsecond resolution. And so that's something being worked on at the very moment, but at least has been demonstrated to work. And just to skip through a few images, now this is another nice, again, breakthrough actually of the last couple of months, because this is now the low band range. This is 50 to 70 megahertz. Again, in the old days, you had just, you would have had one big blob and 10 Jansky or so sensitivity. The best one actually was at the VLA recently, so they got down to 100 millijansky. And now we're here at about 4 millijansky RMS in this field with 20 arcsecond. And you see sources all over the field. This is 55 megahertz. This is 40 megahertz. This is 30 to 40 megahertz. So we can go as low as 30 to 40 megahertz, which is close to the ionospheric cutoff. One other thing to just very brief, you don't see much. This is a movie, actually. A movie of 7 pointings on the sky. This was made to look for transients. That's one thing that runs in parallel with all these, you see every LOFA pointing will have sort of thousands of images in there, and then you're going to look for transients in those things, something that flares. Disappointingly, of course, nothing flares in this movie, except for a little bit noise at the edges. But on the other hand, it actually shows that the imaging is rather stable. You actually would see any transient that would have flared up here within 20 minutes. So that's good. Now, of course, the big important thing and topic of LOFAR is the epoch of reionization. And that is essentially, to some degree, similar to what I mentioned at the beginning, this radio recombination line, spectral line studies. But now we're not looking at radio recombination lines. We're looking at the spin flip line of the hydrogen atom, the famous 21 centimeter emission, 1.4 gigahertz. And if that's redshifted by a factor of 10, then you would see it in the LOFA band at about 140, 120 megahertz. What would be at redshift 10, 11, and so forth? Well, that is the onset of star formation. And if you look at the evolution of the universe was filled with hydrogen after the Big Bang. It has cooled down. It had recombination, hydrogen, and dark matter. That's it. Dark matter clumped together. Hydrogen would follow. And then at some point, the first stars and galaxies would come about. And that would start to ionize the entire universe. And then you can look at what that would do with hydrogen emission. And you would see, for example, in what's called the dark ages, when there were no stars at all, you would see sort of some absorption, actually, of H1 emission. If you go higher, you would have sort of some initial heating, and then reionization, you go from emission to from absorption to emission. And that's something you could detect with LOFAR. That's sort of one of the holy grails, so to speak, now to go into the epoch before you had the first galaxies, to measure cosmology there. That is an extremely challenging project. It is by far not easy. It's being attempted as we speak. The telescope is now pointing days in a row at particular fields. These are several fields they've picked, in particular the North Celestial Pole here. And that is sort of a deep image from last October. This 15,000 times 15,000 pixel. You cannot even show that on a projector. 8 by 8 square degrees and 140 microgensky noise in October. And you need to go about 10, 20 microgensky. So you need to just keep integrating. And you're interested not in the sources, but in everything that's in between. That's where you would like to see fluctuations in the background from hydrogen and H1. And so the nice progress is now, after 70 hours, the noise has gone down to 44 microgensky, following exactly square root of t as you expect, which means you have no systematics left. There's also no interference disturbing. So you're really on route towards a detection of H1. What you also see very nicely is just this improvement of sensitivity, where there were few sources in between, see many little sources pop up in there. Again, so that completely changes actually the way you do radio astronomy. Again, when I did radio astronomy 15 years ago, there was literally one source you look at. In every field there was one source. And now you have really thousands of sources. Okay, I'll come towards the end. Just briefly mention, of course, the other things, the super solar system studies. This is Jupiter's torus. That's actually being observed again this week, I think. This is a nice solar flare observed at low frequencies. In fact, I think at these frequencies, no one ever before has imaged a solar flare. That's what our friends in Potsdam are doing at the very moment. That is the first as well. And then my computer should work on. And then at the very end, I'll just want to mention very briefly the ultra-energy cosmic rays, which is a completely different application of the LOFAR phased array technology. The basic idea is, all these, typically actually these radio jets I was showing are a big candidate for those at the highest energies, or supernova explosions. You accelerate protons and iron nuclei, probably in shock acceleration, which bombard the Earth as cosmic rays that we see. When they hit the Earth's atmosphere, they produce a shower of secondary particles containing lots of electrons and positrons. Those electrons and positrons will rush through the Earth's magnetic field. They will be deflected, and actually will make a coherent radio flash within 20 or 30 nanoseconds. So you get a very short flash on the sky when a cosmic ray hits, but it has to be above a certain energy threshold. And that's built in, and because we have our cosmic ray detector, we also have sort of pulse detectors in our radio antennas built in, and we can read out the buffer boards from the individual antennas. And what you then can do is you can monitor or see individual pulses in every antenna, and you can measure, for example, when does a pulse arrive where. So this here is now a movie. This is in hundreds of nanoseconds you see here. This is when the pulse was seen at different antennas in the superturb, rushing over here. But I say rushing, but essentially what determines the speed here of propagation is the speed of light, right? So this thing rushes with the speed of light more or less over this the superturb. And that's what you measure, and from the sort of time delay, you get the direction of where this pulse came from. And you can measure, for example, what you can measure here is the intensity of the radio emission as a function of separation from where the cosmic ray hit, where you see that this actually is flat and then falls down. I should say this is by an order of magnitude the best sampled curves of this form. In the old days you had maybe 1 or 2, 10 or 20 of these points. You wouldn't see the shape. Now we see very nicely the shape of the emission. We can image this. Now this is an image made with a single station. This here is zenith. This is zenith. This is a horizon here. And you see here a point source flashing up. Again, this movie takes 200 nanoseconds or so. And so for 20 nanoseconds, you see a bright flash, Giga-Jansky flash at the sky. And that's where the cosmic ray hit. We know this from the particle detectors that this is there. And in fact, we were prototyping this early on in LOFAR, testing some of these ideas at Karlsruhe with the Cascade array. So that allows us to detect cosmic rays. That allows us to get an energy spectrum. So that's what you see here, an energy spectrum of cosmic rays. You see we have sort of a power law here at above 10 to the 17 electron volts and then extending further. That will grow. This year it will be less efficient. And what you see here is the arrival time of this shower as a function relative to a plane wave. And so what you see here, that this thing does not come in as a plane wave, but it has curvature. And that curvature you can think of as a sort of non-plane wave. I mean, if something is in the near field, you have a non-plane wave. Yeah? And from that curvature, you can determine what the height is, where it came from. And typically, these things come from a couple of kilometers in the Earth's atmosphere. That's what you expected. From that curvature, which I think has never been measured again so well as in this plot, which again is just a few hours old, you actually should be able to get where the maximum of interaction was in this cosmic ray evolution. So proton comes in, protons, electrons are being generated and then die out again. And where the maximum of this evolution is related to this curvature and related to what particle it was. A proton penetrates very deep into the atmosphere, takes all its energy. An iron nucleus breaks up and sort of makes many little showers and gets stuck somewhat higher. So that is one way you want to get the composition of the ultra-energy cosmic rays. And I'm skipped in the final 10 slides and come to my conclusion. I hope I've tried to convince you that LOFAR works. In fact, better every week, as I said, which means it was a lot of work before, because it is a rather complicated machine. It actually took a lot of. And in fact, it was mainly, I think, the young guys who made a big impact. Many postdocs, even PhD students, who had a lot of impact on the project, working diligently through many of these bugs that were there to go make this improvement from 2 years ago to now, which now really gives you high-quality data. We're now running Cycle 0 science projects. So they've gone through a normal science peer-reviewed project, peer-reviewed process. It's running at 30% efficiency, which is exactly what we had expected at this moment. There is actually going on a multi-snapshot sky survey, which will try to cover all sky. There's an EOR project. There's a lot of transient pulsar searches at this very moment going on. For pulsars, we already have learned a lot. I mean, really, I think many pulsar models, I didn't show them all, have a lot of trouble now with the LOFAR data. I didn't mention, we actually surprisingly see lots of millisecond pulsars, which is unexpected. That's very good news for pulsar timing arrays. ISM studies, actually you see everywhere, you see sort of the effect of the interstellar medium, at least in the galaxy, of course, not everywhere. Radio recombination lines are actually much better visible than I had thought. It's actually, it could become a very interesting, I mean, it could turn out to be completely uninteresting. We just don't know. Again, we just started this at this very moment. Imaging surveys are certainly very promising. I mean, every pointing has 4,000, 6,000 sources in there. And what's very important, what I find important, in the old days, I think you would have one radio flux in a LOFAR survey, in a radio survey. You had beautiful quasar surveys with spectra and colors and so forth, and had 1.4 gigahertz radio flux. Now you get a spectrum, you get curvature within the band, you get 1.4 gigahertz to low frequencies, you get morphology at a good resolution because many of these sources are actually resolved. So you get much more information, I think, on extragalactic objects. And in addition to that, of course, you have galaxies, galactic structure, Sun and Jupiter. Epoch of ionization, the big goal of LOFAR, of course, that's surprisingly good on track, I should say, because even some of us wouldn't bet on that to succeed. We can still hit some snatch somewhere, but at the moment, the noise keeps decreasing, and sort of we are not that far away from, well, it's still many hours, hundreds of hours more integration, but in principle, it seems possible to do this. And then again, these cosmic rays, completely different application of just using individual antennas. Again, I think It's quite an unusual application. And also something that I skipped allows you to do fast radio transients from astrophysical sources. If something flares on the sky for a very short moment, and there are nowadays a couple of reports where people say we found a very short radio flare at cosmological distance, something like gamma ray burst in the radio, just lasting for milliseconds. But it's very unclear what this is, where it does come from. You know, having such a technique, if we can catch those, we can tell whether it's local, because we can actually tell where it comes from, or whether it's actually from beyond well beyond the Earth's the geostationary orbit, where satellites are. We get actually all kinds of other information from it. And that lets me conclude my talk with the last sentence and pointing that other things are going on as well, like city studies and ionospheric studies and lightning. And if you have some ideas you want to test out, the next call was expected in summer, and then there is open time, there is German time, so there's ample opportunity to get involved. Thanks a lot.
I would like to open the questions first to students. Any students have questions?
So as I understand it, the main limitation of the number of sources you can observe once is computing power.
Sorry?
As I understand it, the main limitation of the number of sources you can observe once is computing power. Right?
One of the main limitations at the moment is indeed computing power, yes.
So we're making quite good advances in computing power, so is it reasonable to expect, say within a few decades, that we will be able to more or less observe every direction in the sky all the time, and then just post?
Well, we're discussing, this of course is sort of the pathfinder for the SKA, and we hope that some of them makes it into SKA, for example, but there of course you go often choose for more sensitivity. If you want to have more sensitivity, then you have many more antennas, then your computing power goes into more antennas rather than all field of view. But yes, indeed, if you just constrain yourself to just the innermost core, we actually at this very moment, actually colleagues of mine in Amsterdam building a correlator to do all sky, essentially all frequencies all the time, but with poor resolution. And not maximum sensitivity. So yeah, that is going to happen. And LOFA as well, we're going to upgrade its computing power, certainly the correlation and so forth in the coming years, actually pretty soon. Yeah. So it's not the limit. In fact, we also bandwidth has increased. Initially, we just had 33 megahertz bandwidth at 120 megahertz. Now we have almost 100 megahertz. So just because of progress of technology, and that's the maximum we can use. So we are now at maximum bandwidth.
Beautiful data. So a question about the expected Rayleigh emission in M87 that you showed here.
Yeah.
I do not think that is too surprising, because if you basically take into account the collisional cooling by Coulomb interactions, you actually find that the maximum cooling time of electrons of the order of 30 to 50 mega years, if I did the calculation correctly. So basically, you're not sensitive to any time scale beyond this, because all the electrons that cool this bottleneck down to the thermal plasma, because you have gas density order of 10 to the minus 2 in the center of Virgo. So I think that is not too unexpected.
That's interesting. I haven't been aware of the quantum cooling. I think that could play a role in the bubble.
Coulomb.
Yeah, sorry. I doubt it would explain the absence of relics, because the relics actually usually sort of open up and become very, very tenuous, and then it would not be so
effective.
effective.
Mixing, basically.
Yeah.
You mix the stuff into the ICM, or whether this stays there coherently as a
Yeah, so I think that to describe M87 bubble, that, more effects will play a role. The absence of relics, I think, is difficult. But again, the answer is not. That's why I say I'm not entirely sure what it really means. So I'm just a little bit puzzled at the moment.
And another question about this fan region.
Yeah.
So you described the technique of Faraday rotation, but if the source and the screen is actually mixed into each other, which the ISM is, so that you basically emit and at the same time you actually rotate, so that the lambda square law does not is not anymore like the square law. So did you check for the absence of the Lambda?
That's why this was a poor man's explanation. That's Faraday rotation synthesis, which actually sort of unfolds these different components. So if they are different depths, this actually recovers that. So you actually you do something like cleaning in interferometry for different Faraday depths. So in principle, that should work. If you have enough sufficient data.
Does it work already?
Sorry?
Does it work?
Yes, yeah, you saw it. It did actually. I mean, you actually get a different. I mean, you would not have seen that bubble actually, because that, you know from the shape on the sky, this is sort of a ring-like structure, and you actually see it also in 3D. So that works out very well.
Okay. I have a basic question on what you call observations. If I understand correctly, the antennas observing the whole sky all the time.
No. Yeah.
And then, what's the next scenario in your observations?
Good point.
Kind of like calculators, or storing the data, or analyzing the data?
I mean, all the antennas produce terabits per second all the time. You cannot process this. Well, you can, if you do process this, but you cannot do all sky, all frequencies all the time. That was your dream, and mine as well. Right? So I'd love to see that. So what you do is you combine sort of the 48 antennas in one station into, you just add them up essentially, which selects one direction. And that is predetermined by putting in a delay between the antennas. We say, okay, I want to look in this direction, so I add them up as if the emission comes from that direction. And I could do it a second time in another direction, but that costs more computation power. If I want to do all sky, I have to do it sort of 10,000 times. 10,000 times. And that we can't do. We can do only 8. So, is that clear?
Yes.
Sort of. Yeah. So you throw away data by beamforming, essentially. You throw away sky.
You showed a lot of images with quite a number of unknown sources, and of course you have your radio spectrum, and you can then try to determine the nature. How good is actually the astrometry of wave leader sources?
Yeah, there were some offsets of a few arcseconds in the last couple of months, which we had to find out. Honestly, I'm not 100% sure how good the astrometry is down to this arcsecond level, but certainly on 10 arcsecond level, so it seems to be okay. In the end, it should be actually excellent. I mean, the biggest problem is the ionosphere, but you always have a reference grid of known sources which you can pinpoint it to. So
I want to push much deeper to microarcsecond.
Microarcsecond you cannot do with low frequencies. I think you can get to milliarcseconds or so. It's going to be essentially 100 milliarcsecond divided by signal to noise. That's the maximum. So maybe you can get 10 milliarcseconds or so. Microarcsecond you have to do it with ALMA VLBI or so. Yeah. Sorry.
So you just touched on the imaging service for the solar system. Is there anything with the increased sensitivity that we found in our solar system that's surprising?
No, not yet. I mean, actually, that's essentially the first things we've done. So we're going to look at Saturn. We're going to look at Venus. Look for lightning, for example. And there was some tentative things, but we're not sure about this, and so we're going to be more sensitive measurements of weather on solar system planets. That's for sure. And we're going to look at exoplanets as well. So actually, again, in the next couple of weeks, there'll be pointings on certain exoplanets to see low-frequency Jupiter-like flares. And Jupiter makes bright flares. Still, it's going to be hard. I mean, it has to be exceptionally bright to see exoplanet flare.
Yes, so how sensitive would it be? Would it have to be like the same level as Jupiter?
No, it would have to be much brighter than Jupiter. So
100 times, 1,000 times?
I don't know the exact number, but it would have to be Jupiter, a hot Jupiter close to it, and then assuming there's a scaling law which assumes that the radio emission proportional to the momentum impacted of the solar wind impacting into the planet, which is very empirical. So and untested.
Is the 21 centimeter line at high redshifts is probably against a very strong background and foreground. What do you expect to see? The emission line or absorption line?
Actually, both. This depends on which redshift you are. You start with sort of absorption, and then you go into emission again, sort of in this process. And this is essentially this balance between CMB photons and the thermal state of the gas. And you have fluctuations. You're going to have fluctuations from the ionization centers around galaxies.
So that's what you're going to look for. You look for the power spectrum around 140 megahertz, which comes from the first galaxies ionizing the H1. Well, of course, for discovery you have to have 7, right, or 10. Well, I mean, as I said, you need to go to about 10, 20 microgenskis for current models. Currently, we have 44 microgenskis, so that requires square root of maybe it's almost a factor of it's 4 more, so 16 more observing time. So that's about 1,000 hours. That's not too much. I mean, it's for cycle 0, it's a lot, but over the course of the next 2-3 years, this is going to be okay.
You mentioned free absorption briefly.
Yeah.
If you go down to very low frequencies, is there any prospect of detecting the IGM through free absorption, for example, through capacity effects obscuring the background sources, these background radiogases?
I think IGM free absorption is going to be hard. But for example, if we would see one of these flares, if one of this radio gamma ray burst, so to speak, were to be discovered here, we would see Faraday rotation and dispersion. And that would give us the density and the magnetic field in the IGM. And so that would give a lot of information out of this source. So free absorption, I think free absorption is very strong in the galaxy, and we know this. It's going to be important. H1 regions will H2 regions.
Galaxy groups,
yeah. Yeah, maybe galaxy groups. I don't know. Yeah, maybe galaxy clusters. I haven't thought about this. So it's worth checking. I mean, the home density is clear, so maybe a little bit. A little bit of effect should be like the Sunyaga-Solovich effect, more or less, right? So for cluster.
See if we did a change in the number counts of source per square degree, see in certain directions compared to others.
Yeah. Okay, now there's something to explore. Maybe there are people who want to do just cosmology just with the number counts of radio sources, so that's certainly interesting.
Last question?
Obviously, with such a versatile telescope, the random space is kind of complex, but what's actually more interesting if you want to expand parameter space? Building more telescopes or buying more computing power?
You need to do both. the cheapest, the easiest is of course more computing power. That's going to happen. In fact, we're discussing, more computing power at the central facilities. That is actually his prime goal right now is more computing powers. Actually, in our university, we bought our cluster just for Lofa data reduction. Others have done the same. So that was sort of one way of expanding this. The central computing will be expanded. For getting instantaneous sensitivity, more stations and more antennas will of course be useful. Yes. To some degree, this is going to happen at SKA, where you have more sensitivity.
Okay, so